Welcome to this explainer. Today, we're diving into the incredibly cool world of federated learning. If you've ever wondered how artificial intelligence is evolving to actually protect your privacy rather than compromise it, you are in exactly the right place. We're going to unpack the mechanics, the math, and the massive implications of this technology. So let's kick things off with a question I bet you've asked yourself at some point. How do tools like predictive text on your phone or voice assistants like Siri learn your specific habits, your accent, your frequently used words without uploading your entire private life to a massive server owned by some tech giant? It feels like a total paradox, right? Smarter AI usually means more data, but somehow your personal data is staying on your device. Here's our roadmap for today. First, the AI privacy problem. Second, enter federated learning. Third, the federated workflow. Fourth, cross-device versus cross-silo setups. Fifth, Fed SGD and Fed AVG. And finally, the federated learning challenges. All right, Section 1, the AI privacy problem. Picture a decentralized data setting. We've got this immense amount of data scattered across millions of local devices. Your phones, your tablets, your smartwatches. And each of these acts like an individual database with its own privacy lock. Historically, to train an AI, you'd have to crack all those vaults open and dump that raw data into one centralized cloud. Doing that obviously destroys data privacy and ignores the limits of local hardware. We desperately need a way to preserve those privacy locks while still getting a globally smart AI. Which brings us to Section 2, enter federated learning. So what exactly is federated learning? Well, the crucial takeaway here is that multiple clients collaborate to solve a problem, but each client's raw data is stored locally and never exchanged. Seriously, let that sink in. The raw data stays locked on your phone. Instead of moving all of our personal data up to the machine learning model in the cloud, federated learning completely flips the script. We move the model down to the data. And the crazy thing is, you're probably using this literally right now. Take Google's Gboard on Android. It uses federated learning to predict your next word. It learns that you always type umami burger after sure, but it does this without ever sending the actual content of your text messages to Google's servers. Your texts stay yours. The keyboard just gets smarter. But it goes way beyond predictive text. It's revolutionizing high-stakes fields like healthcare, too. Through initiatives from companies like Intel, hospitals can actually share AI model updates to detect diseases better. They collaborate to build a global diagnostic model without ever exposing sensitive, legally protected patient records to the outside world or even to each other. The privacy locks stay firmly closed. Okay, Section 3, the federated workflow. Let's look at how this happens. Let's break down exactly how this magic trick is pulled off in a 5-step workflow. Step 1, initialization. Your locked private device, acting as a client, reaches out and downloads the current global AI model from the central server. It's basically getting a blank slate, the baseline intelligence that the server currently has. Step 2 is where the real innovation kicks in. Your device uses its own local private data, your texts, your photos, your voice commands, to train and improve that global model right there in your pocket. It's essentially studying your habits in strict isolation. Step 3, the upload. But here's what's absolutely critical. Instead of sending your raw data back, your phone sends back only the homework. It computes the mathematical gradients, the specific adjustments the model needs based on your data, and sends only that updated mathematical model back to the cloud. Finally, in steps 4 and 5, the central server acts like a conductor. It gathers all these tiny mathematical improvements from millions of devices, aggregates them together, often just by averaging them out, and uses that massive collection of insights to update the new global master model. Then the cycle repeats. Everyone gets the smarter model, but nobody shared their personal secrets. Moving on to Section 4, cross-device versus cross-silo. Now, not all of these setups are identical. There's a pretty stark contrast between the two main environments here. On one side, we have cross-device federated learning. This is what's happening on your smartphone or smart home devices. We're talking millions of clients, massively parallel but highly unreliable. People turn off their Wi-Fi, batteries die, signals drop. On the flip side, we have cross-silo federated learning. This connects a small number, maybe 2 to 100, highly reliable dedicated servers at major institutions like banks or hospitals. Understanding which environment you're building for completely changes how you have to engineer the network. All right, Section 5, Fed FSGD and Fed AVG. Let's peel back our final layer and look right under the hood at the mathematical engines powering this. There is a massive difference in how these two approaches communicate. With FedSDG, the device is constantly bouncing information back and forth to the server in real time. But with FedFAG, the device executes several local practice loops entirely on its own, offline, before it ever reports back to the server. To put that into plain English, think of it this way. FedSGD, or Federated Stochastic Gradient Descent, tells the server what it learned after every single flashcard. It's very chatty and uses a ton of bandwidth. FedAVG, or Federated Averaging, on the other hand, is way more efficient. It studies the whole deck of flashcards multiple times locally, doing multiple local training epochs, before finally taking the test and sending a combined average update to the server. FedAVG is the industry standard because it drastically reduces how much your phone has to talk to the cloud. But, that efficiency is a delicate balancing act. The foundational research proves that FedAVG's performance relies heavily on specific hyperparameters. You have to balance the number of participating clients, the number of local epochs, or how much local homework they do, and the local mini-batch size, which is basically how much data they chew on at one time. If the devices practice locally for too long without checking in, their models diverge way too much from one another, and the global aggregation just becomes a mess. Which brings us to our final section, Section 6, Federated Learning Challenges. As brilliant as this all sounds, engineers face daily battles to make it actually work. Yes, preserving privacy is the goal, but ensuring those mathematical model updates don't accidentally leak information is a constant fight. Then there's the immense communication cost of transmitting complex neural networks over mobile networks. Plus, we have data heterogeneity. Everyone's data looks totally different. Some text a lot, some don't at all, and system heterogeneity, the chaotic nature of spotty internet connections, varying phone processors, and unpredictable drop-offs. It's literally a logistical nightmare. And even when you dig into the heavy convergence math in the source material, the final proofs basically boil down to this. The success of the model, how fast it zeroes in on a smart, accurate solution, depends directly on handling that data variety, carefully tuning how much local practice happens, and managing how efficiently the network communicates. If any of these variables are out of whack, the AI simply won't learn. Which leaves us with a truly fascinating, paradigm-shifting thought to end on. If your own phone is doing the heavy computational lifting to train the world's most advanced AI models in total privacy, is the era of tech giants hoarding our personal data in massive server farms finally coming to an end? Federated learning isn't just a clever algorithm. It might just be the blueprint for a future where AI gets smarter and our private lives stay private. Thanks so much for joining me on this explainer. I hope this gives you some awesome food for thought.